Hi everyone, welcome to my quick little video covering mathematics for EC 102. It's going to focus predominantly on derivatives. Just keep in mind these tricks when you're doing things like problem set number 2 and problem set number 4 from part 1. As far as derivatives go, as far as I can tell, they will only be really needed for those two problem sets. And of course, graphical analysis can always help with these things if derivatives are proving too difficult for the analysis that you need to do. Nonetheless, a lot of you have asked for this video, so I'm going to make a short video just covering the basics of how to take a derivative, what we're talking about when we talk about the derivative of a function, and the usefulness of this particular skill. The slides that you can see in front of you, I'm going to upload as well as this annotated version, which I'm going to draw on and do some practice problems as we go. So let's move on. As I said, we're going to cover rates of change, the notation for taking derivatives, the rules of how to turn a function into its derivative, why derivatives are useful, and focus a bit on partial differentiation when we have more than two input variables in our function. The point of a derivative is that it's going to give us information about this something we call rate of change. When we have a normal function f, we're just going to call the function f. The function always takes some kind of input, and then the function spits out some kind of output. So quite often we express this particular relationship between input or inputs using tables. We might have an x variable as an input, a y variable as an output, and we can show some numerical relationship between these two by specifying at particular x values what the output value or the y value would be. We also use pictures and graphs where we have the output variable on the y-axis and the input variable on the x-axis, and it just shows some relationship between these things visually. But predominantly what we want to talk about in this particular presentation is how to represent the relationship between these inputs and your output using an equation. And a really basic example of that is when we have y as our output variable and maybe x plus 2 as our input variable. So when x is 1, y is 3. When x is 2, y is 4, etc. Very often when we talk about this, we talk about this in terms of the function of x. So f, which takes x as the input, is specified using mathematical notation as x plus 2. But this also can be read as just the output being defined by the function x plus 2. So that's going to give us our output y. We're not always just interested in what this output is. Sometimes we're interested in how this output changes as we change our inputs. So we'll talk more about that in the next slide. We see we've got a visual representation of a function in this slide with x and y on the respective axes. The rate of change for a particular input level is given by this, the tangent line. The slope of this line is defined as the distance, as the rise over the run. So in this case, the slope would be 2 over 3. Notice that this value 2 over 3 is obtained when we have the input value of a, and this value 2 over 3 is not our output value, but it's the rate of change of this input, which is a very different thing altogether, although there's obviously some relationship between these things. So the slope of the tangent line at a given point, in this case the answer should have been equal to a half. Let's make that 2 over 4. So then the slope would have been 2 over 4, which equals a half. We say that a half is the instantaneous rate of change. That should be a positive. The notation we use for the instantaneous rate of change at a particular value is often this one, f dash a. The dash denotes that it's not the value of the output that we're interested in at the value of the input a. We're interested in the rate of change of the output at the value a. We also sometimes use this notation, which we'll see a lot more. But again, this is just a concept where we're taking the same input, A, let's let the input be A, and now we're not interested in the output at the value A, we're interested in the rate of change of the output at that particular value. Let's move on. Here we have another function represented graphically. We see at the input value 1, the output value is 2, but the rate of change is given by the slope of this line here. For an input value of 4, the output value is 3, but the rate of change is given by the slope of this line. And likewise, for an input value of 7, when we feed that into this function, the output value looks to be about 2.5, but the slope of that rate of change at the input value of 7 is given by the slope of this line here. So here, using our notation from our previous slide, we have that df dx at an input value of 1, this slope here, equals 1. df dx at an input value of 4 equals the slope of this line here. The slope of a line that's perfectly flat is always just 0. And here we have a downward sloping tangent line, which is defined here as negative a half. This graphical approach is limited in its use, as with most things in mathematics. When we start to talk about multiple input variables, 2 or more input variables, it can become quite difficult to look at the rate of change of the output variable just by looking at a 2D graph. We're also limited when we use a graphical approach to calculate the rate of change by the fact that we can't display all the points along the x-axis. We can only show so many, and we might want to know something in general about how this thing behaves as we change the input, how the instantaneous rate of change or the derivative of the function behaves for a wide range of inputs. So what we want to do is not rely on the graphical approach. We want to rely on some set of rules that allows us to turn the function itself which takes inputs and spits out outputs. We want to now create something that takes x as its input value, and when we feed it through it, the output value now is not the value of the function at x, but it's the value of the derivative or the instantaneous rate of change for a given x. We'll talk more about that in a second. As I said before, we have x's as our input, we have some function, and that function spits out y's. Now we want to have the same x's as our input, but instead of spitting out y's, we want this thing to spit out dy dx, or the rate of change, the instantaneous rate of change. And the process of going from this function to this function is called taking the derivative of this function. Taking the derivative. The process is called deriving or taking the derivative. Sometimes we denote this as f dash, but we'll talk more about notation in the next slide. When we have a function f, which takes x as its input value and turns it into y an output value, we call the function that takes x in and spits out the rate of change of this function as either f dash x, df dx, dy dx, del y del x. Notice the slight difference between these two d's, but they're essentially the same mathematical notation when we talk about a function with only one input variable, and we sometimes see this as well. The one that I'm going to use in this particular video is the one that we have used throughout the macro course, which looks something like this. So when you see this, all you should think is that we're now trying to define a function that takes x as input and gives out the rate of change of the function fx as the output. So let's learn some rules that allow us to start with a function and find df dx. Again, the function df dx is just going to take x as its inputs and spit out the rate of change at that particular x input. It itself is going to be some kind of function. And we're going to talk about the rules that one can apply to try and turn this object into this object. The first rule we're going to talk about is called the power rule, which says that if we have some initial function that takes inputs and spits out outputs of this form, where a and n are some real numbered constants, then the derivative of this function, df dx, is always given by, first of all, multiplying the function by this exponent n, bringing that out the front here, then writing x to the power of n minus 1. So an example we have here is fx equals x squared. How would we find the derivative of that function? Df dx. In this case, if we have a 2 as the exponent, we take that out the front, so we multiply everything by 2. We then write x to the power of n minus 1. In this case, we have 2 equal to n, so 2 minus 1 is just 1, but anything to the power of 1 is just itself. So the derivative of this particular function here is 2x. We could also practice the power rule from this particular function. We see the function now is 20 times x to the power of 1 over 20. Now, df dx, we take 1 over 20 out the front, 1 over 20, multiplied by 20x to the power of 1 over 20 minus 1, which is going to be negative 19 over 20. We can see that 1 over 20 times 20 just equals 1, so the derivative is x to the power of negative 19 over 20. And whenever we have a negative exponent, we could also just write that as 1 over x to the power of 19 over 20. We can turn a negative exponent into a positive exponent by taking it to the bottom of a fraction. Let's move on. We're now going to talk about rules for dealing with functions that have addition and subtraction inside them. So now we look at this function, fx equals x squared plus x cubed. Using the power rule and this addition and subtraction rule, we just take each component individually. So what's the derivative of x squared? We showed in the previous slide that it was 2x. Now we just apply our power rule to x cubed. We take the 3 out the front. We minus 1 from 3, and that's the new exponent. So the derivative of this whole function is given by this. So when we encounter addition and subtraction, we just treat the terms separately, we derive each one separately, and then we have our new function which takes the input x and spits out df dx, or our derivative. We also have something called the product rule, which is used in a situation where we have a function that can be expressed as the product or the multiplication of two other functions. So we can think about these kinds of cases as pertaining to situations when we could identify two different functions within this function. So for example, if we have a function like this, we can think about, in this case, the function g as being this guy. We can think about the function h as being this term. And then we can think about how to apply the product rule, because we can rewrite this function now as gx times hx. The product rule simply states that if we have a situation where our initial function can be written in terms of the product of two other functions, the derivative of that initial function is given by the derivative of the first subfunction times the second subfunction underived, plus the derivative of the first subfunction multiplied by the first subfunction underived multiplied by the derivative of the second subfunction. So in this case, let's move to the next slide to solve this particular problem. We had that g of x equaled, let me just remind myself, g of x equaled x to the power of 3. We had h of x, which equaled x squared plus x. So if we take the derivative of the g subfunction, we use the power rule to get 3 out the front times x to the power of 3 minus 1, which is 2. If we use the addition rule and the power rule for the h subfunction, the derivative of the h subfunction dx dh equals 2x, because we brought this 2 out the front, and 2 minus 1 was the power 1, which is the same as just writing x, so 2x. We then use the power rule to derive this part of the h function, because these enter as additive terms. So back to our addition rule, we just treat them as separate, and we use the power rule on the first term and the second term. So the derivative of x, this one we have, is a little bit different. We can still use the power rule by thinking of this as x to the power of 1. So if we take that 1 out the front, multiplying something by 1, and we subtract 1 from the exponent, 1 minus 1 is 0. But remember that anything multiplied by 1 just equals itself, and anything to the power of 0 just equals 1, which is why when we take the derivative of x, we have a 1. So the product rule now says that if we combine this thing, and the definition of our original subfunctions, we then have df dx is equal to the derivative of our g subfunction, 3x, times our original h subfunction, x squared plus x, plus the derivative of, the original g subfunction, x cubed, times the derivative of our original h subfunction, 2x plus 1. And if we wanted to try and tidy this up a little bit, we could just notice that we can take out x3 as a common factor in both of these, and we get this. But this last step is more playing with manipulating equations rather than taking derivatives. So that's probably something to be discussed in a different video, or indeed something to be reviewed on your own using something like a Khan Academy. We talked before about what happens when you take the derivative of x. So whenever we see an x, we can think about it as being x to the power of 1. So the power rule just suggests that the derivative of this is 1 times x to the 0, which equals 1. Now we're going to think about the derivative of a constant. So if we have a function like this, which is represented by a, the constant, plus some other subfunction hx, then the constant in this case is just going to disappear when we take our derivative, or in other words, the derivative itself is equal to h dash x, or in our notation, the derivative of f of x is just equal to the derivative dh dx. So just visually speaking, why is this constant, this additive constant, not impacting our derivative? Well, just look at figure 2 here. Look at this example. The additive constant is just going to be a shift in the curve along the y-axis. Shifting the curve doesn't change the slope of the function at any given input value. So for a value x, the slope of the function f of x is this. The slope of the function a plus f of x is also this. And these slopes, when we calculate the rise over the run, are exactly the same. So the function itself would give different output values when we have a given input value. At x, the output value of the first function is here, the output value of the second function is here, but the derivatives are exactly the same, which is another fancy way of saying these lines are parallel, if they have the same slope at any given point. Let's move on. We have one more rule to consider, which is the chain rule. Doesn't really come up too much in what we've covered, but just for the purpose of being complete, I thought I'd cover the chain rule as well in this video. If we have a function f of x that can be written as some other function that contains another subfunction, I'll be more specific about examples of that next, then we have a special rule, and we call that the chain rule. So looking at this example, f of x equals 1 minus x cubed, all raised to the power of 5. The first step is to write this as some function of another function. So let's define h of x as 1 minus x cubed. We now see that we could rewrite this as 1 minus x cubed to the 5, or h of x all to the 5. we're going to define the g function as taking the input value u and spitting out the output value u to the power of 5. So now we can see that if we used the g and the u notation, then f of x would just be g on the outside and then the subfunction h of x on the inside. The rule for these types of problems require us to recognize that the derivative of the entire function df dx equals the derivative of the function inside another function multiplied by the derivative of the outer function evaluated at the initial function. That's all probably pretty complicated, and I know that I'm going quite quickly in this video because it's meant as a refresher. But of course, if at any point you have any problems, feel free to just do something like Google or search on YouTube for the chain rule, and it will give you plenty more examples. Let's do one example now, just to try and help this concept dig a little deeper into your brain. In our example, we had f of x equaled 1 minus x cubed to the 5. And we said that we're going to define h of x as this internal part, 1 minus x cubed. We're going to define g of u as taking the input u and raising it to the power of 5. So we need to first take the derivative of each of these subfunctions. First of all, the derivative of the g function is using the power rule. We bring 5 out the front. This was 5, we bring 5 out the front, we subtract 1 from the exponent, so 5 minus 1 is 4. So the derivative of the g function is this. We then talk about taking the derivative of the h function, or the function within a function on our right-hand side here. The derivative of 1 minus x cubed should be 1. We're going to use our addition and subtraction rule. Let's derive 1. The derivative of 1 is 0. We showed that constants don't have any impact on the derivative. So we have 0. The derivative of negative x to the power of 3 is negative 3. 3 comes out the front, to the power of 3 minus 1 is 2. Again, just applying our power rule. We now need to use the chain rule to put it all together. The derivative of our original function, df dx, equals the derivative of our g function evaluated at our underived h function times the derivative of the h function. So let's see if we can put all that together. This last term here, dh dx, we just got from this step here. So we're going to have something times negative 3 times x to the times x squared. The term out the front, remember, was the derivative of the g function evaluated at the h function. So when we say evaluate, what we mean is we sub in the h function, f of x, into this. So where u is here, we just have to write the original value of f of x, of g of x, of h of x, which is 1 minus x cubed. So the derivative of the g function was 5u to the power of 4. So we're going to replace that u now with 1 minus x cubed. So this should be a 4. There's a mistake here. 1 minus x cubed inside this derivative of the g function. I know this is getting quite messy. It's because I'm trying to rush through it, but of course, remember just to pause and have a practice if you need to. Again, I'm not sure how essential the chain rule is going to be for EC 102, but just for the purpose of this being all-encompassing, the chain rule is kind of the last step we need to think about when we learn the basic rules of taking derivatives or differentiating. We again can kind of simplify this up a little bit to get the result here. But again, this should be to the power of 4. Let's move on. Some other quick rules to remember when we take derivatives is the derivative of the log function is always 1 over x. The derivative of e to the power of x, or the exponential function, is itself again e to the power of x. So using the chain rule, using the product rule, using the power rule, and just remembering these identities, we can more or less derive pretty much any continuous function that we'd encounter in most economic applications, particularly in undergrad. So those rules, if you can master those, basically mean that you've mastered taking derivatives or differentiation. Here are some functions to have some practice on. Most of these come from the course material. Let's do this one, because that comes up a lot. Let's imagine we're trying to find the marginal product of capital. This is, of course, a production function with capital and labour as the input variables. If we want the marginal product of capital, marginal product with respect to capital, we have to derive this thing with respect to k. So we let the L be fixed and we focus in on the k. The derivative here, if k is to the power of 1 over 3, we take 1 over 3 at the front. We subtract 1 from a third, which is going to be negative 2/3, and it's all just multiplied by 2 over 3, because for the marginal product of capital, we're taking a derivative with respect to only the input variable k. So in this particular case, what we're talking about is a partial derivative, where we only think about one particular input variable as changing, and we think about how that changes our output variable. Let's move on. Here's just a quick rundown of the different available resources. My favorite book on this stuff is this one, which is available in the library at LSE, Essential Mathematics for Economics. Again, this is a good resource to get a whole bunch of questions, and it also goes through all these rules, etc. Please don't invest too much time in learning derivatives if this is completely new to you. Maybe spend a few hours or even a whole day on it, but the problem sets are not going to require you to take derivatives beyond, sort of examples like this, or I think problem sets 2 and 3 and a little bit of 4 use derivatives. But again, the first step should be to try and graph all these relationships and try and think about just the math itself. The derivatives can be useful, but for this course, there are probably more important things to spend your time on, especially given that it's an intensive summer unit. But if you really need some more pointers and you've looked at these resources and nothing's making sense, of course, send me a quick email or just come and see me after class. So having learned all these rules, and hopefully some of them have sunk into your brain or been a refresher from high school, let's have a look now at why derivatives are useful. First of all, we can use them to describe a function. We can also use them to find points of interest, which we call extrema or maximum and minimum points, but we'll talk more about that in a moment. Why is it useful to be able to describe a function in terms of its derivative or its rate of change? Well, for instance, if we knew that the derivative was always positive for any x value, the derivative was always positive, what does that mean? It means the rate of change for any x value, if we have y here, the rate of change or the slope of the tangent line for any input x value, if that's always positive, it means that the graph must always be upward sloping. Because at any given point, the rate of change or the tangent line is a positive line. So it might have kind of weird looking dips and things like this, but we know immediately that as x increases, if everywhere that we have an x, we have a positive instantaneous rate of change or a positive derivative, then as x increases, always our output y must increase as well. So that's what it means to have a strictly positive derivative for all different inputs x. The opposite is true, of course, if we have a strictly negative derivative for any input x. As x increases, if the derivative is strictly negative, it must be a downward sloping function, because at any input value x, the slope is negative. So as x increases, our y must be going down. So that's something that's quite interesting. In economics, it's always good to know whether the function is obtaining a higher output value or a lower output value as our inputs get larger. Let me just get rid of some of this because it's getting a little bit messy. Some other things that are interesting are when the value of the derivative starts negative and then is always increasing as x increases. So let's look at an example of that. The value of the derivative starts negative. So we have a downward sloping function at some input value. Then the derivative is always increasing as x increases. So if, let's say it's increasing in the sense that it's getting less and less negative. So let's start with this kind of curve. It's getting less and less negative. The rate of change is going from a big negative number to a small negative number. If it's always increasing, at some point it will turn around, and now we have the function increasing in x. That probably wasn't the most neat way of saying that, but we often call this property convexity. We can also say that if a derivative starts positive and then gets lower and lower, we have a function that might look like that. So initially we're upward sloping, we're then sloping upward at a lesser rate, we then turn around at some point, the function's going down, the derivative goes from being big positive to 0 to big negative. We call that property concavity. Again, this is kind of beyond the scope of what you need to know for this course, but it's something that's kind of going to come up again and again, so it's good to just have seen these terms at least once before. Another reason we like taking derivatives is because we can use them to find these extrema points. One of the cool things about derivatives is that if we're given some function, we often don't exactly know what value y is our maximum value. That might be a little bit weird to think about, but if I'm using some kind of numerical methods and I just plug in an x value and it spits out a y value, I have no real way of knowing whether that's the biggest y value that I can find by choosing my x to maximize y. So actually I may plug in this particular x value, it spits out a particular y value, but I may not know that I have found the maximum value. So y can be all different values when we think about the maximum. There's nothing intrinsic about an output value. So let's say y equals 10. We really don't know if that's going to be the maximum or not, because of course different functions are going to have different maximum values. We're going to have all kinds of crazy functions. So one thing we like about the notion, the concept of derivatives of continuous sort of smooth functions, is that we may not know anything about the y value at the maximum, but we do know something about the derivative at the maximum. The derivative at the maximum, if we have a nice smooth function, is going to be 0. Right? The point at which we are no longer increasing, but we've only started to decrease instantaneously, is going to be the maximum. Or likewise, if we find a derivative of 0, the slope of the line is 0, again that's true of a horizontal line, we also might be at the minimum point. We might have just stopped decreasing and we're about to start increasing. The derivative at that point is 0. So we know something about when our functions exhibit turning points, or maximum or minimum or extrema. We know that the derivative at that point is 0. So working backwards from setting a derivative equal to 0 and then solving for x can be very useful, because it can find the important points in our function that map into maximums and minimums. Let's move on. I think I already spoke about this slide, so let's not worry too much. And I think I've probably covered everything. I'm not going to go into optimization in this class. Let me just quickly scoot through the slides. Is there anything else I want to talk about? Let's just quickly talk about functions with more than one input variable. So this now is a function of x and y. It spits out the output value z. Another function that we just saw before that has more than one input variable is our Cobb-Douglas production function, where labour and capital are both inputs, and production y is our output. In these cases, we just need to be a little bit more precise about our understanding of derivatives, particularly because the rules that I've showed you don't don't give us much information yet about how to kind of think about multiple input variables. But what we're going to do is we're going to talk specifically about something called partial derivatives. And the partial derivatives are really easy. It's simply the process of deriving the function with respect to one particular variable only and treating everything else in there as a constant. So you could very easily, for example, if you had y equals k to the power of 0.5, L to the power of 0.5, if we wanted to find the partial derivative with respect to k, which is again going to give us the marginal product of capital, when we take this derivative with respect to k, we can basically just think about this L to the power of 0.5 as being a constant. So let's just rewrite this, and let's let c, little c, be some constant. I mean, the constant term doesn't really matter. We think about that as being a constant. How would we approach this thing using the power rule? We take 0.5 out the front. We subtract 1 from the exponent. So we left with 1, with 0.5 minus 1 is negative 0.5. And then we multiply by this constant again. Again, the constant was what? L to the power of 0.5. So let's just substitute that back in, and we now get our partial derivative with respect to k of this particular function. So anytime you see there are more than one input variable, you can always just think of one input variable as being exogenous or a constant or a parameter of the equation, something that we're no longer interested in varying. We fix that in stone, and then we only focus in on the variable of interest, i.e. we take a derivative of a particular function partially, or with respect to just one variable. In this case, if we let y squared equal a constant, x squared plus the constant here is our sort of new function. If we derive this with respect to x, dy dx, no, whoops, that's not going to work, sorry, df x y dx. We apply the power rule to this term, bring the 2 out the front, subtract 1 from the exponent, so that's just 1 or x itself. We then look at the addition rule. So plus a constant, we were told earlier that when we added a constant to a particular function, the derivative didn't change. So the derivative of this constant is 0, so we're done. And no need to substitute the constant's value y squared back into it because the constant was totally erased from the equation. These are some practice examples that you can do for yourself, but I think probably I've already gone a little bit beyond what you will need for this course. The most important thing I would say for this particular course is just to understand doing derivatives of this kind of thing, or in other words, just making sure that you're comfortable applying, in particular, the product rule, being able to deal with constants, knowing that the derivative of a constant is 0. Again, the product rule is probably super important, knowing how to deal with addition and subtraction in our initial function when it comes to taking the derivative. And I guess, more generally, just understanding what a derivative is. It's a way of expressing a function not in terms of the outputs y, but in terms of the rates of change dy dx. Yeah, so that's all we're trying to do. We're trying to turn some function that spits output out when we give it some input into another function that spits the rate of change of the output out for the same set of inputs. I think that just about covers it. I know I've been quick, so please pause, go back, shoot me emails if you have any questions, and don't forget the resources that I talked about, Khan Academy, and where did I talk about those resources? I think somewhere down here. Sorry if this cruising through the slides like this is confusing your heads when I'm watching the video. Here we are. Khan Academy is a great one. Other YouTube videos, for example, just search for Power Rule. Essential Mathematics for Economics by these two authors. Any kind of high school textbook that covers or sort of basic calculus. And the tool that you would have seen me use in class a lot, which is Wolfram Alpha, which is really good for checking answers and helping visualize certain functions. I'm going to wrap it up there. Don't forget to email me if you have any problems, p.j.lambert@lse.ac.uk. I hope this was helpful. Hopefully it jogged your memory back to when you did this stuff in high school or in some calculus course in undergrad. Hit up the resources if you want to focus more in on it. And all else failing, don't get too worried because the course really only about 10% of it kind of uses this type of math. Good luck for the rest of the course. Thanks for listening.